Okay, Algebra 1, so here is the next video. So now we're going to focus more on comparing our data sets, and we're also going to use Desmos to try to find some values here. All right, so our first question says, the points of each player on Parker's basketball team for the season are shown in the table. The points of an opposing team are represented by the box plot. How does Parker's team compare? So what we're going to do here is we're going to use the numbers in the table, right? Parker's teams. We're going to create the 5-number summary to then make a box plot if we wanted to, and we're going to compare the medians and the IQRs. Okay, that's what we're going to compare. Because when you do a box plot, we're going to compare the medians and the IQRs. Okay, so let's first look at the opposing team. So the opposing team is right here. So this is the opposing team. And for the opposing team, their median is right there at 474, right? This is the median. Sorry. Okay, so their median is 74. And their IQR is going to be their third quartile. So this is their third quartile, 76, minus their first quartile, 73. So we're doing 76 minus 73 is 3, right? So again, the median is 74 and the IQR is 3, which means, right, that most of their players, the middle 50%, are scoring right around 74, maybe down to 71, 72, up to 75, 76, right? So again, very centrally located there. All right, so now we're going to do Parker's team, and we're going to do this on Desmos, okay? So when you use Desmos, right, whenever they give you data, you're going to create a table. So we're going to add a table. We're going to put all of our data in X1 column, and it doesn't matter the order. So I'm just going to put it 32, 35, 32. You can press enter or just arrow down. 60, 80, 36, 90, 45, 76, 96, 92, 100, 120, 60, 38, and 75. Okay, so we have that data, and that is in the X1 column. So now, a very important command that you should try to remember for Desmos is stats. If you click on the keyboard, it is over here under functions. There's a lot of statistics things, but there's this stats command. So you can click on it, or you can just type in stats and press in a parenthesis. So what this is going to do is this will give you the 5-number summary, okay? And then I think it also gives you the mean and maybe the standard deviation, we'll see, of the data in X1 as long as you type in X1. And let's see. Nope, it just gives you the 5-number summary. But that's all I need, right? I just need that 5-number summary. So now if I take a look at my data here, okay, do it in blue. So this is for Parker's team. Sorry, Parker's team. So his median is 75, and the IQR is going to be 92 minus 38, which is roughly 54. So if we compare that to the opponent, so the opponent had a median of 74 and an IQR of 3. So although Parker's team's median is a little bit higher, their IQR is way bigger. So I would say that for Parker's team and the opponent team, I would definitely say that Parker's team's scoring is much more variable. So Parker's team's scoring has higher variability. So when we talk about spread, that's how the data varies. And again, like I said, typically we want our data to be very focused on the middle. So with an IQR of 54, that means if I divide that by 2, I get 27. That means that they could score like 40, 75 minus 40, 27 is like 48, all the way up to like, what, 102, something like that. So again, much more variable. Okay, lacks consistency, if you will. All right, very good. Okay, next question. Okay, there we go. Here we go. Okay, so it says the label on a cereal box says the weight is 12 ounces. The dot plot shows weights of 2 random samples of 16 boxes packaged at 2 different machines. How can you compare the data sets to see if there is a problem with one of the machines? So what we want to do is we want to kind of take a look at these 2 dot plots. We're going to find 2 things. We're going to find the standard deviation, the mean, and we're going to find the standard deviation. Okay? And we're going to use those 2 numbers to kind of compare the data. Okay? Actually, we're going to do the mean, and then we're going to do the range, I think. Okay? I'll show you everything. Okay, so let's take a look at these dots. Now, each of them have 16 boxes. So what we need to do is we need to input each dot as its number. So like these 3 dots all are going to be 11.8s. So when I type them in decimals, I'm going to type in 11.8 3 times. Okay? So again, I have my data off to the side. So I'm going to do that right now. Okay, so let me clear this table. Let me clear this. Let me get rid of that table. Okay, so let me get rid of the table. All right, so let me add a table. All right, so again, so for that first dot plot, machine A, so we have 3 11.8s, an 11.9, two 11.9s, 12.0, 4 of them, 3 12.1s, a 12.2 or 2 of them, 2 12.2s, a 12.3, and a 12.4. Okay, so I have the data there, right? So again, I can use the functions to find a couple different things, right? So I can find the mean, I can find the standard deviation. Now, again, this is more than you need to know, but this P stands for population. This is a sample, so we would just use standard deviation, okay? So let's do the mean. So what is the mean of X1? Okay, so the mean of this machine A is 12.0375. So I'm going to put that right over here. So that's pretty close to 12, right? We want every box to be 12, and we right now are at 12.0375. So for A, the mean is 12.0375. And now let's do the standard deviation. Again, the book also uses what's called the mean, or it's called the MAD, the mean absolute deviation, but it's the same thing. So for standard deviation, it's over here. I think it's in the way sometimes. I apologize. So we'll do functions. Again, standard deviation here of X1. And there we go. And we get 0.178. I'll just round to 3 decimals. So what that is telling you is that is about how far the data averages from that mean. So your standard deviation is 0.178. So again, your boxes vary by about 0.178 ounces, from the mean. Okay. All right, and now we're going to do the same thing, but we're going to do A. I'm sorry, so machine B. So let me delete that. Let me delete that, if I will. Okay, delete that, delete that. Okay, so now we'll add a table. And again, it takes some time to enter the data, but again, so we have 3 11.5s. We have an 11.7, 11.8, 11.9, 3 of them, 2 12.0s, 2 12.1s, 2 12.2s, a 12.3, a 12.4. All right, we're done. Yeah, right. Let me just double check. 2 12s, 12 1s, 2 12.2s, a 12. Okay, very good. Okay, so now I will do the same commands. So I'll do the mean. I'll just do them both at the same time. So mean of X1, and then the mean, and then the standard deviation. Okay, so now if we take a look, right? So for machine B, we have a mean of 11.9375 and a standard deviation of 0.28, should round up to 3. So if we look here, right, we want these boxes of food to have 12 ounces. A is overshooting it by a smidge. That's okay, right? The consumer's not going to be mad. But B, this machine is going under the 12. If you consistently produce data under 12, that's a problem, right? The consumer's going to be mad. Plus, your standard deviation is a little bit higher, right? You're about 0.28 ounces off per box. So I would suggest that because B's mean is less than 12 and it has higher variability, again, that's the measure of spread, the variability, higher variability, because B's mean is less than 12 and it has higher variability, B might have a problem. Might have a problem. And there you go. Okay, perfect. All right, 2 down, 3 more slides to go. All right. Next. Okay, so it says, it says customers of a bagel shop complain that some bagels weigh less than the amount of the label, 90 grams. The manager generates a second sample. What does the shape of the histogram for the second sample tell you about the data? So if we take a look at this second sample right here, right, this sample right here, shape, right? So if we look at this, so we have this data, which is going to be skewed to the right. So if you take a look at that, look at where the tail is. The tail is on the right side. So this data is skewed right. Because it is skewed right, that means that the mean is going to be dragged to the right, meaning that the mean will be bigger than the median. That explains why the mean height is bigger than the median height. And again, based on this sample, I would say that the customers cannot complain right now, right? But again, it's because you have some of these high outliers that are weighing higher. Because if you look at the sample, there were 8 that were less than 90. But because of all of these over here to the right, it makes the mean seem bigger than 90. So again, just this idea of skewness is important. Okay, and then the next one says, suppose the quality control manager adds another 10 bagels to the third sample. If 5 bagels are 78 grams each and 5 bagels are 106 grams each, would that affect the mean and median weights explained? So if we take a look here, right? So if I look at this histogram, 78 is going to be less than this last bar. So I'm going to add a bar of size 5 right here. I'm going to do the same thing over here with the 106 because the 106 is bigger than 104. I'm going to add a bar of size 5 right there. And now, to begin with, this graph was roughly symmetric. But now when you add the ends and they're both the same, it is still roughly symmetric. So because the sample is roughly symmetric, the mean and median are going to be about the same. And because you add a little bit on each side, each end of the data, it is not going to change. So the mean and median will still be about 90 grams. Okay. Next. Okay. So it says the data display shows the heights of 50 randomly selected males from the US, Netherlands, and Indonesia. What is the shape of each set of data? What does that tell you about the data? Okay, so if you take a look here, right? So we have the height of US males. This data is skewed to the left. If you take a look at this histogram, we are going here, right? The tail is on the left, so this is skewed left. I'm sorry, this thing will not let me write by it. So this is skewed to the left. Because it is skewed to the left, that means that the mean will be less than the median because it's dragged to the left. So again, I would say that in this histogram, the median is somewhere there and the mean is somewhere over here. Okay, for the Netherlands, I would suggest that this data is roughly symmetric, right? So for the Netherlands, it is roughly symmetric. So therefore, I would suggest that the mean and median are about the same. So the mean equals the median. And again, I would suggest it's right around here, right in the middle, around 84. And now for the box plot, you cannot like draw the hump, but again, you can notice that the whiskers of your box plot, right, used to be called a box and whisker plot. You can see that the whiskers, the right one is much longer. So this is definitely skewed to the right. Skewed to the right. And because it is skewed to the right, that means the mean will be bigger than the median. So we know the median is right here, right? That's the median. So I would suggest the mean is somewhere probably over there, a little bit to the right. So shape, mean, median comparison. All right, last slide here. Last year, 12 hydrangea bushes had a mean of 14 blooms each with a standard deviation of 2. The dot plot shows the number of blooms on the same bushes this year after a new plant food is used. What conclusions can you draw about the use of the new plant food and the number of blooms? So we have a new set of data to compare to an old set. Again, this old set has a mean. So this is last year's. So I'll do last year. So there was a mean of 14 blooms with a standard deviation of 2. So now we're going to use Desmos to find this year's mean and standard deviation. Okay, so let's go do that in Desmos right now. All right, so I'll delete all my stuff. Okay, so if I add all my data, and again, each dot represents the number. So we have 8, we have 2 12s, we have 2 17s, 3 18s, 2 19s, a 20, and a 23. Okay, so there's my data, right? So again, I want to find the mean of that data, and I want to find the standard deviation. Now notice, I'll show you in the functions. So this they don't say this is a sample. They say that these are the plants from this year. So we have to use this standard deviation P for population. Again, you're not going to remember that. It's okay, but I'm just going to tell you that's the best way to do it. Okay, so here for this year, right? We had a mean of 16.75 with a standard deviation of 3.94. So again, if we compare that to last year, which had a mean of 14 and a standard deviation of 2. So obviously, you can see that the new plant food has helped, right? The mean, the average has grown to by 2.75. So the new plant food produces, on average, more blooms per plant, but with, and now we have to compare the variabilities, the standard deviation, and notice that standard deviation was almost double, right? So now we're less accurate, right? So what this new plant food's doing is it's giving you some high producing ones and some lower producing ones. So we're going to say the new plants, I'm going to say the new plant food, sorry about that, produces on average more blooms per plant, but with higher variability. Variability. And there you go. All right, so thanks for watching. Hopefully this helps. Good luck on your practice on Stavis. Make sure you take the notes. 3 videos for homework. Last set of videos of the year. Last time getting my annoying voice. Congratulations.